let's look at sample test 2 for Physics 214. Number 1, find 1A, the period of a wheel, find the following. The period of a wheel with radius 0.5 meters, it rotates 5 times each second. So the period T is the time for one revolution. All right, and so we have here that we have, it takes, in 1 second, it goes around 5 revolutions. All right, so that tells us time per one revolution. And so that is like 1/5 of a second. Whoop, that should be seconds. And so 0.20 seconds is the period. All right. We could also take 1/5 or 5 is the frequency, and T is 1 over F, and get it that way too. All right. Find the speed of a point on the outside edge of a wheel of radius 0.5 that takes 10 seconds to make one revolution. All right. So we want speed, which is meters per second. All right. And so we need to know how many meters does it go around, does it take, is it when it goes all the way around the wheel? All right, so the wheel is a circle, so the radius, the circumference of a circle then would be how far the outside point is moving in one revolution, right, going around the whole circle. And so that's going to be 2 pi r. And then in how many seconds? So this says it takes 10 seconds to make one revolution. Right, oops. One revolution, 10 seconds. All right, so how many meters? Okay, so that's how many meters per revolution times how many revolutions in 1 second. And so we're going to have 2 pi times r, which is 0.5 over 10. And this is meters. And so we end up with meters per second. Plug that in. 2 times pi times 0.5 divided by 10. All right, so 0.314 meters per second. Not very fast. I mean, 10 seconds to do one revolution is not very fast. So we only have actually one significant digit, so 0.3 meters per second. All right, find the centripetal acceleration needed to make keep a car going 25 meters per second around a curve of radius this. So the centripetal acceleration is caused by friction, holds it in from going off the side. So our circular motion equation that we need to remember for acceleration, v squared over r is the required acceleration. Some force needs to be pushing in, remember, into the center of the circle. Your car is going around here on the road or whatever. Centripetal acceleration is into the center. We've got a velocity of some sort. V is the tangent all the way around. And then, of course, r is the distance to the center of the curve, center of the radius of the circle. All right, so just plugging in stuff, we got it all just given to us here. 25 meters per second over 100 meters. Everything is in the correct units, so we can plug in. Get 6.25 meters per second squared. Looks like 2 sig fig, so 6.3 meters per second squared. Alrighty. Number 2, looking at gravitational forces here. We've got a bunch of information in terms of the mass of the moon, sun, earth, radius, distance between things. So let's look at what we need. Gravitational force with which the sun pulls on the earth. So for this one, we're going to need the equation for gravity between bodies. And so that's capital G, m1, m2 over r squared. In this case, capital G, mass of the sun, mass of the earth, divided by distance from sun to earth squared. All right, so the radius is the distance between the two things. So we got G 6.67, 10 to the negative 11. What is it? Newton meters squared per kilogram squared, I think. And then mass of the sun, 1.99 10 to the 30 kilograms. My fat marker, I'm running out of room here. Mass of the Earth, 5.98 10 to the 24, and then divided by the distance between the Earth and the Sun. Center to center is what we want. 1.5 10 to the 11 squared. All right, so plug that all in. 6.67 negative 11 times 1.99 negative 30 power 10 to the negative 30 power 5.98 10 to the 24, and all that divided by 1.5 times 10 to the 11 squared. All right, so I put it in the right form there, so that's good. So we end up with 35 and 10 to the 21. Everything was in kilograms, meters, the correct units, so this should come out to be newtons. So 35 times 10 to the 21 newtons. Alrighty. Similar kind of thing, force that the moon pulls on the Earth. So again, same big G constant, but now we're going to have mass of the moon, mass of the Earth, divided by distance moon to Earth squared. 6.67 10 to the negative 11. Mass of the moon, 7.35 10 to the 22. Mass of the Earth, we just had it, 5.98 24. And then we can divide it by distance from the Earth to the moon, 385 10 to the 6th squared. Plugging all those in. And so this calculator is nice. It kind of shows you, make sure you get your fractions right. In terms of putting in parentheses or not to put in parentheses, you can check to see if you got it right. And so it looks good there, I think. And we end up with 198 10 to the 18 newtons. We have 3 sig figs everywhere. It looks like that's okay. 198 times 10 to the 18th newtons. Okay, next one. Same kind of stuff, planets and distances and masses, but this one it says find the distance between a planet with this mass and the sun if the force that the sun pulls on it is this. Okay, so we're going to rearrange the equation. We got the force is again G, mass of the sun, mass of the planet divided by distance, sun to planet, squared. But now we're looking for the distance. Right, and so you could put in your numbers first or do the algebra first. It's going to go do the algebra. So distance sun to planet is going to be, bring this to the top, divide through by the force, take the square root. So it's going to be G, mass of the sun, mass of the planet, divided by the force. All right, so you can take a few steps to do that out, work that out, and see if you get the same thing, but I'm pretty sure I got that right. So the distance is going to be square root of 6.67 10 to the negative 11. Mass of the sun, 1.99 10 to the negative, or 10 to the positive 30. Mass of this unknown planet, 10 to the 1.9 10 to the 27. And divided by the force, 417 10 to the 21. So let's plug all that in. Square root 6.67 negative 11. 1.99 to the 30th, 1.90 to the 27, divided by 417 to the 21. Alright, so we get 778 times 10 to the 9th. Everything was in standard kilograms and meters, newtons, so this one will then be in meters. Alright, so 778, 10 to the 9th meters. Alright, so that's page 1. Get this here. Page 2. Free-body diagram for each of the masses below. Include forces, acceleration, direction, coordinate axes, and x and y components of vectors. Alright, car rounding a corner on the road with mu sub s equals 0.8. So we've got car going around a corner. Alright, so we'll have the centripetal force acceleration going in. We'll have some sort of velocity going around the corner. We're given mu sub s, so it gives us a hint we want to talk about friction. So we'll draw the, for this one, the interesting view is looking at it from behind to see the friction and the force that way. So we'll draw the car from behind, big wheels for some reason, okay, because of the friction. So we always have mg, and it's sitting on a road, so it's got a normal force. And then the thing that keeps it going around the circle is friction, so keeps it from going off the side. So we have friction straight into the center of the circle. Let's have some x and y components. And we'll have our acceleration has to be into the center of the circle to keep the thing from flying off. Alright, everything is lined up with x and y, so we don't have different components from sideways with angles, and so that should be good for that one. Alright, car going with constant speed over a hill. So we got a hill, a round hill, radius 150. And we got our car going this way now, over the hill. So we'll look at the side view of the car this time. So side view of my car here. Alright, so again, mg, sitting on the road, so it's got a normal force. Constant speed, we aren't told about friction, we aren't told about thrust, so we'll just assume somehow it's going constant speed. We don't really know stuff about the sideways forces, so we'll just have that much, I guess. We'll have x and y, and then the acceleration always to the center of the circle. In this case, acceleration then is straight down. Okay. Tetherball swing around a pole on a rope that makes 10-degree angle below the horizontal. So we got a pole, got a rope, we got a ball swinging around, and then we get 10 degrees down here like this, and the ball is going around the pole. Alright, so we'll do a free body diagram. We've got mg, we've got the tension that the rope is pulling on the ball with, and so we have 10 degrees here, so it'll also be 10 degrees here. Need our x and y components. We'll have, again, the circle is around the pole, so the acceleration is right towards the pole. So AR would be this direction. And we need components here, so we got the x component, we call it tx, I guess. This whole thing is t, and this will be ty. Something along those lines. Okay. Number 4. The work done by a person carrying a 10-kilogram box up 3 flights of stairs okay, yeah, some typo. 3 flights of stairs, say ending up 10 meters above where they started. So basically what's going to happen is you got a box, and as far as the problem is concerned, what happens is the box goes up 10 meters. Right, so that's the distance traveled, or the distance that the force acts. And we've got mg, and then the force that the person is using to lift the box up. We'll assume that it goes up at a constant speed. So we don't have any acceleration, so that means that the force is just equal to F. So the net force is F minus mg, and we'll say, since it's constant velocity, we'll say it's equal to 0, no acceleration. So then F equals mg. And so we can get our work, F d cosine theta, and F is straight up and D is straight up, so theta is 0. So F is straight up, D is straight up, so that means theta is 0 degrees. That means cosine theta equals 1, so that means the work is just F times D, and F is mg. Okay, running out of room here. So then the work is just mgd, so m is 10 kilograms, g 9.81 meters per second squared, and d is 10 meters, just straight up. So the work, I'm going to steal a little space here. The work is 10 times 9.81 times 10, pretty much 100 times 9.81. Anyway, 981 joules would be my work. All right. Part B, work done by gravity on a 1,500 kilogram car driving 100 kilometers on a flat road with an engine thrust of 400 newtons. The work done by gravity. All right, so we got a car, and it goes a distance of 100 kilometers. It's got a thrust, 400 newtons. It's got mg, and all right, and so it says the work done by gravity. Okay, kind of a trick question, I guess, because D is here, right? 100 kilometers horizontally. Mg is straight up and down. So the angle between these two is 90 degrees. So theta is 90 degrees. So that means cosine, so work, of course, remember, is FD cosine theta. But theta is 90 degrees, so cosine 90 degrees is 0. So the work is 0. Okay. The force is perpendicular to the motion, to the displacement, so no work is done by gravity. The thrust, on the other hand, would have work, but that's not what it asks for. Okay, number 4, kinetic energy of a bowling ball rolling 4 meters per second. Kinetic energy, we like kinetic energy because it always has the same equation. That's easy, 1/2 mv squared. All right, so 1/2 mass, 5 kilograms, velocity, 4 meters per second squared. So we'll plug everything in. .5 times 5 times 4 squared, we get 40. Kinetic energy is in joules if we got all of our units right, which we did. So there we go. Force needed to accelerate a 5 kilogram bowling ball from 0 to 5 meters per second in 2 seconds, assuming constant acceleration. So force, let's do force equals ma, Newton's second law, right? Because we've got stuff to find acceleration, we've got the mass. Let's find the acceleration. So A average, or just the A, we're assuming constant acceleration, is going to be delta V over delta T, right? How fast it speeds up in a certain amount of time. So it's going to be 5 meters per second final velocity minus initial velocity, which was 0, ending time 2 seconds minus beginning time 0. So it's just going to be 2.5 over, 5 over 2.5. So acceleration is 2.5 meters per second squared, 5 halves. All right, so we can plug that in. We got the mass, 5 times 2.5, 5 kilograms, 2.5 meters per second squared, gives us a force of 12.5 newtons. We really only have one significant digit, so let's just say 13 newtons. Okay. The work needed to accelerate a 5 kilogram bowling ball from 0 to 10 meters per second. All right, so this one has velocity. We're asking for work, so remember we have the work energy theorem. So the work applied is equal to the change in kinetic energy, is one version. All right, and so we're looking for the work, so we need to can find the change in kinetic energy, which is Ke final minus Ke initial, which is 1/2 mv final squared minus 1/2 mv initial squared. Initial velocity is 0, so this term goes to 0, and so the work is just 1/2 mv final squared. 1/2 m is 5 kilograms. mv final is 10 meters per second. So 0.5 times 5 times 100. So the work is 250 joules. Work applied. All right. Find the velocity of a 2.2 kilogram wooden block if the 30-gram bullet hits and embeds in it with a velocity of 500 meters per second. All right, so this would be a completely inelastic collision. Remember, we're talking about momentum kind of things here when we're talking about collisions. So completely inelastic is when two things, it starts out as two things and then they get stuck together and they move as one thing after that. So the bullet embedding would qualify as they're stuck together after that. So remember, conservation of momentum, it just says momentum before the collision equals momentum after, and momentum is just mv, right? And so we could say mass A times this velocity in the one condition, mass B times this velocity in the one condition is going to be equal to, in the second condition they're stuck together, so they're one mass. We'll just call it MA plus MB because the two masses are stuck together, and then they just have one velocity. We'll just call it V2, the velocity of the two condition. All right, so let's just go ahead and plug in numbers at this point just so we can see it easily. And so we'll call A the wooden block. All right, and then so MB is the bullet, and the bullet is the thing that has a velocity of 500 meters per second. The block is sitting still, so this would be VB1, and VA1 would be 0 since the block is not moving. All right, so we've got MA1 2.2 times 0. Everything is in, well, not quite standard units. And so let's get the mass of the bullet needs to be in kilograms, so 0.030 kilograms times the velocity is in good units, meters per second, equals the two masses added together, so 2.2 plus 0.03, all that's kilograms, and then V2 is what we're looking for, so we can't write that one down. All right, so plugging that in, 0.03 times 500, so this is 15 equals 2.23 kilograms times V2, so V2 2.23 divided by 15, 0.149 meters per second. Let me just double check myself when I did this before. We got a different answer. What happened? Oh, bad algebra is what happened. Okay. Divide through by the 2.23 over on this side. So V2 is 15 divided by 2.23. 6.73. So 6.7 meters per second for V2. Alrighty. Part G. Find the final velocity of a 28-gram pickleball, initially going 10 meters per second after it hits a stationary 100-gram golf ball and causes the golf ball to have a velocity of 4.37 meters per second. Okay, so this is another collision kind of thing. So when we hear collisions, things bumping into each other, think about momentum. Think about momentum, MV. This one is elastic collision, most likely. Anyway, we don't really need to worry about the kinetic energy, but for elastic collisions, remember momentum and kinetic energy are conserved, but we have lots of information here, so I think we can just get it all with the momentum. So we got mass A times its first velocity plus mass B times its first velocity is going to be mass A times its second velocity plus mass B times its second velocity. All right, so mv plus mv equals mv plus mv for conservation of momentum. Okay, so we'll just call the pickleball A and the golf ball B. And so let's just put stuff in here. So we need kilograms, so we'll say 0.028, and the pickleball is going 10 meters per second. This is kilograms. Plus the mass of the golf ball, 0.1 kilograms, and it is stationary, so its velocity is 0, so that term's going to go away, equals mass of the pickleball, 0.028, times its final velocity, that's what we're looking for, VA2, plus the golf ball mass, 0.100 again, and then its final velocity. The golf ball has a velocity, yes, 4.37. Alrighty, so we can bring this to the other side. So we'll have 0.028 times 10 minus 0.100 times 4.37. 0.028 VA2. VA2 then divide through by the 0.028. 0.028 times 10 minus 0.1. However you like to do the algebra. 0.028 is 10 minus 0.1 times 4.37. All of that has to go on top. Divided by 0.028. Negative 5.61 meters per second for VA2. So it's negative, so that the negative means it's going backwards. So a light ball hits a heavy ball, bounces off, the one ball goes one direction, one ball goes the other direction. So that makes sense. Alrighty, how fast can a 1,500 kilogram car go around a flat circular corner, radius 75, mu sub s equals 0.75, uk equals 0.5 without sliding? So this is kind of like the free body diagram we did a little bit ago. We've got a car going around, going at a velocity around a corner, has a radius 75 meters, and have acceleration into the center, like we always do with circles. And it's friction that's causing that acceleration into the circle. So we want to know how fast can we go with this amount of friction, the maximum speed we can go, basically. So we're just going to calculate the maximum, use the maximum value of friction, and without sliding, so that means we're not using mu k because that's the sliding friction. We're using mu s, and we're going to figure out the speed. All right, so let's do a free body diagram looking from behind the car. You got to think about the frictions going sideways, so the friction is going like this. We got mg, got n, x and y, acceleration straight to the left. All right, so we'll do our f. Let's do y first. In the y direction, we've got n going up, mg going down, and that's it. So that's going to be equal to may, but we want it to be sitting flat on the ground, not going up in the air, so ay has to be 0. And so this is going to say that n equals mg. All right, we're going to need n for calculating the friction. Let's just go ahead and calculate it now. All right. $1,500 times 9.81. Although the mass probably would cancel out, so maybe doing this a little bit ahead of time, but we'll just go with it. 720 newtons. All right, so that means the force of friction then. We can use the standard formula, mu sub s times normal force, and so that's going to be 0.75 times the 14,720. So take what I had there times 0.75. I get 11,036. We'll say 11,040 newtons for the force of friction. Oh, I'm running out of room. Okay, now we need to sum F net in the x direction to get our acceleration and things figured out. So in the x direction, all we've got is friction. And it's going in the negative x direction, so I need a negative sign in there. And then we have the equals max, but ax, acceleration in the x direction is negative ar, or ar is in the opposite direction of it than x, so it's going to be negative ar. That's an r. And so that tells us that the force of friction is equal to m times ar. But we got a circle going on here, so that we know ar, acceleration, is our handy dandy circular speed acceleration equation, so it's v squared over r. And that's good because we're asked how fast, so that means what is v? Okay, so let's plug that in for ar so that we can solve for it. And we know r is 75, and we know force of friction, so we can kind of plug in everything here. So we got force of friction, 11,040, equals the mass, 1,500, times ar, which is v squared over r, 75. Okay, so we can solve for v. Take a couple steps if you want to. If you need to, is good. 11,040 times 75 divided by 1,500, square root of all that. Okay. Like the velocity is about 23.5 meters per second. Okay, so remember the static friction is up to mu sub s, and mu sub s, where that's the maximum static friction we can get, so that's the maximum speed we can get without the car starting to slide off. Alrighty. Yep, that's what I have. Letter I, the apparent weight of a 1,500 kilogram car going over a hill with radius 150 meters. So we got a car going this way now. Alright, so we got the acceleration is straight down to the center of the circle. That's got some velocity over the hill. So again, we're going to have our a sub r is v squared over r that we're going to need. We need a free body diagram too. Let's just go ahead and do that. So we've got mg, we got n, and that's pretty much it. We're not given information about what's making the car go that velocity, so it's just somehow going that velocity, but we do have AR going straight down. Okay, so we can plug in and get AR. It looks like we got everything. 25 meters per second squared over the radius, which is 150 meters. So 25 squared divided by 150. So 4.17 meters per second squared. Doing our Newton's second law, so we can relate acceleration to our forces. So we've got F net in the y direction. We got N going up, mg going down, equals mass times AY, which is AY is negative AR, because AR is going in the negative y direction. So what are we looking for here? Apparent weight. So the apparent weight is the normal force, how much the earth is pushing back up on you, how much you feel. So we're looking for N. So let's solve this for N. N equals mg minus MAR, or m times g minus AR, factoring out the m. So we've got everything, I think, 1,500 kilograms, g 9.81 meters per second squared, and AR is 4.17 meters per second squared. So we end up with N 8.46 times 10 to the third. Newtons. 8460 newtons, something along those lines. Yes, that's what I had before. Good. Alrighty, number 5. Assume a spring oriented vertically with a 1.4 kilogram mass in contact with one end and the other end held stationary. Assume no air resistance. Sketch the situation with the x equals 0 location indicated and draw the free body diagram. So we've got the mat, so I guess let's draw that. So we've got the spring sitting here. We've got a mass sitting on the spring. And x equals 0 location. Let's just take x equals 0 to be no compression. We're not really, anyway, we'll see what these later parts ask about it, but then we'll take x positive going up. Free body diagram, all we got is the mass, mg, and the spring force, which is the normal force, going up. We'll assume there's no motion in the x direction, or nothing happening in the x direction. And we can assume the acceleration is probably going to be up. Okay, if the spring is compressed by 5 centimeters by a force of 50 newtons, what is the spring constant? So this is kind of a typical problem, or it's like what we did in lab, where you do a little experiment, measure the force and the distance that is compressed, and then you can get the constant from that. So we're going to use F equals negative kx. And so the force is 50. The spring is pushing up, so it's positive 50. And then we've got negative k and then the spring is compressed down, right? So X is negative 0.05 meters, just to get everything in the right units. And so K is 50 over 0.05. (1,000) newtons per meter. All right, what is the potential energy of this spring if it is compressed 9 centimeters? All right, so remember PE formula is 1/2 kx squared. Now that we've got K, we can do this. K is 1,000. X, it's compressed 9 centimeters, so X is actually negative 0.09 squared. Doesn't really matter for this equation since we're squaring it, but we can put it in the negative. So let's multiply that out. 0.5 times 1,000 times 0.09 squared. And so I get the potential energy 4.05 joules. All right. Next part. How much work would it take to compress the spring? How much work would it take to compress the spring 9 centimeters? So we just found the potential energy of the spring. So remember from the definition of potential energy, it is just the work applied. Well, the negative of the work applied. All right, so we push, the work puts in energy and the spring gains the energy. So it's the negative sign of that. And so the potential energy, we're asked for, we have the potential energy, we want the work. So the work then is negative potential energy. And so that's the work applied is negative 4.05 joules. We had that, the potential energy from the last problem. Okay. If the spring is released, what will be the velocity of the mass as it passes the position where the spring is at its normal length? All right, so now we're starting to do some energy balance kind of equations, situations. This is where we'll do, we'll assume we have a lossless system and not talking about friction or air resistance. And so we're going to say KE1, so it's conservation of mechanical energy. Kinetic energy 1 plus potential energy 1 has to be equal to kinetic energy 2 plus potential energy 2. No non-conservative forces. Okay, so we'll say condition 1 is when it's compressed, 9 centimeters, right? And condition 2 will be when x equals 0, when it gets back to the uncompressed, just passes the uncompressed position, right? So KE1, 1/2 mv squared, 1 squared. When it's compressed, it's just sitting there, has no kinetic energy, velocity is 0. So the kinetic energy is 0 for condition 1. All right. Potential energy. What kind of potential energies does this thing have? So actually PE1, it can have potential energy from the spring and potential energy from gravity, because it's oriented up and down. So potential energy is a little more tricky than kinetic energy because it can have multiple sources. Right? In this case, the spring's potential energy is 1/2 kx squared, right? Because it is compressed. Gravity, we need to kind of define where x equals 0. Let's go ahead and just take this as also, x equals 0 is also where PE equals 0. Because we need to define some place as the 0. So we'll just do that. All right, so at x equals 0, potential energy is 0. So in this case, if we're compressed 9 centimeters, the formula for potential energy from gravity is mgh, or mgx, or whatever the displacement is, the distance from the 0. In this case, h is going to be negative 0.09 meters. All right. For the spring, the x is also negative 0.09 meters. Alrighty. So we can get the potential energy here then is 1/2 k was 1,000 times 0.09 squared. Actually, I think we just calculated that, didn't we? Plus the potential energy due to gravity is m. We have a mass 1.4 kilograms times g times our displacement, negative 0.09. So it's okay to have negative potential energy, or part of it be negative. So let's just calculate that in a minute. 0.5 times 1,000 times 0.09 squared plus 1.4 times 9.81 times negative 0.09. All right, so overall the potential energy still ends up being positive, 2.81 joules. All right, condition 2, kinetic energy 2 equals what? Well, always 1/2 mv squared. And that's what we're looking for, is the velocity when it of condition 2, when it passes the normal length. So we'll have to leave that as a variable for now. Potential energy, condition 2, potential energy of the spring plus potential energy of gravity. Alrighty, and so let's see, potential energy of the spring at that point where it's just relaxed, so it's not compressed anymore, and so it's a 1/2 kx squared, but x is now 0. Similar situation for gravity is mgh, but h is x is also 0 at that point, so the potential energy is 0 for this case. All right, so we've got to set these equal to each other. Ke plus Pe1 equals Ke plus Pe2, and so Ke plus Pe1, I'm just going to take this and go up here. So Ke1 was 0, Pe1 was 2.81, Ke2, that's equals, Ke2 is 1/2 mv squared, so 1/2 times 1.4 times v squared plus Pe2 is 0. All right, so just doing a little algebra, v is going to be the square root of 2.81 times 2, all that divided by 1.4. A little small there, but let's plug that in. Square root 0.81 times 2 divided by 1.4. 2. Oops. 2. So v equals 2 meters per second. V2, I think I called it. Sure enough. Okay. How high will the mass go? All right, so now we got a third condition. Condition 3 is top of the flight. All right, so let's do KE3. So we're gonna also, we can just pick which one. I mean, we can just say KE3 plus PE3 has to be equal to either one of the other two. We'll just pick KE1 plus PE1, which we know is just the 2.81 joules, right, from before. All right, so let's figure out KE3 and PE3, and then we can plug them in. So kinetic energy 3, kinetic energy 1/2 mv squared. At the top of the flight, it's going up. We'll assume it's going straight up and coming straight down, so it doesn't have any x component. All the component is y, and the y component goes to 0 at the top of the flight because it's going up and it starts coming down, so it's positive and starts being negative. So this velocity is 0. So kinetic energy 3 is 0. Potential energy 3, it's way off of the spring, so the spring has nothing to do with it anymore, so we just got potential energy from gravity. And what will that be? It'll be mgh. where h is x, what we called x. And so how high will it go? I guess we're assuming how high above the uncompressed height of the spring. Or are we talking about how high above the compressed part of the spring? We'll just say from the uncompressed part of the spring. So we'll just say it's asking for x. All right, so the total mechanical energy then for condition 3 is just mgx, which is 1.4 times 9.81 times x. And that's got to be equal to the total energy from either one of these conditions above, which we got it for condition 1, so 2.81 joules. All right, so x has to be 2.81 divided by 1.4 times 9.81. Yes, okay. So 2.81 divided by 1.4. Yeah, let's get some parentheses in there. 1.4 times 9.81 meters per second squared. All right, so x is 0.205 meters. Probably too many sig figs. Probably 0.20 meters above uncompressed spring. Because that's what we called x equals 0, was where the spring gets uncompressed. Alrighty. Well, I guess rounding it would be 0.21. Sorry. Alrighty, number 6. A 50 kilogram block slides on a surface with kinetic friction 0.111. Let the block have initial velocity of 2 meters per second. Draw free body diagram of the block. Alright, so we've got a block. We've got mg. We've got n. We've got some sort of velocity, initially anyway, and we've got friction. So friction always has to go the opposite direction of the velocity. That's why it's good to go ahead and draw the velocity on there. We've got our x and y, and we'll say the acceleration is probably going to be backwards since it's going to be slowing down. Friction's the only force, and so the acceleration will be that way. So the friction opposes the velocity, but it's causing a negative acceleration. All right, what is the force of friction on the block? Force of friction is mu k times n, since it's sliding, so we need mu k. We need to get n. Going back to our free body diagram here, in the y direction all you have is n and mg. So F net y is n minus mg. MAY, no acceleration, no velocity in the y direction, no acceleration, so n equals mg. And so the force of friction equals mu k mg. We have all these things. Yep. 0.111 times 50 kilograms times 9.81 meters per second squared. So force of friction .4 newtons. 54.45. Let's keep one extra just for while we're calculating. Yep, so that's what we're asked for. What is the force of friction? Okay, I don't know why I did it all over there. I thought I had more stuff to calculate. Okay, find the initial kinetic energy of the block. KE initial. Kinetic energy, 1/2 mv squared. Initial state. So the initial velocity was 2 meters per second. M was 50. Double check that. Yes. Everything is in standard units, so 0.5 times 50 times 2 squared, 100 joules is kinetic energy initial. Yes. Find the final kinetic energy, Ke final, 1/2 mv squared. The final, we kind of need to look back here, or look ahead. So what are we talking about? What conditions are we looking for? We're looking for how far will the block go when it gets stopped. So the final velocity is 0, so the kinetic energy final is 0. All right, how far will the block go? So this, how far is asking for like a d, or a distance, so that maybe gives us a hint that we want to look at the work, because work is force distance cosine theta, and work is also related to kinetic energy. So remember, the work applied, or the net work, is change in kinetic energy. And so friction is the only force, so it's doing all the work. So we've got work is F d cosine theta. In this case, the displacement d was in the positive x direction. The friction is in the negative x direction. So the angle between them, I should draw them. Let's draw them both up on the same level. All right, so the angle between them is opposite direction, 180 degrees. So cosine theta is 180 degrees. Theta is 180 degrees, so cosine theta then becomes -1, right? So the work is just F d times -1. Calculated the F up there, 54.45 newtons. The d is what we're looking for, and -1, and that's equal to the change in kinetic energy, right? Delta Ke, Ke final minus Ke initial. Ke final is 0 minus initial, which is 100. So that becomes -100 joules. So we've got all the pieces here. We can just solve for d. D is 100 over 54.45. D equals 1.84 meters. Probably should just be 1.8 for sig figs. Okay. What is the work done by friction on the block? Well, we just had that up here, the work done. We use that to calculate the distance. So the work done by friction was -100. Joules. Because friction was the only thing doing the work in this problem. Alrighty, number 7. We got a 50 kilogram pterodactyl, 100 and some pounds, flying 50 meters per second. He's going very fast. Okay. Catches a 2 kilogram crow going also very fast. Well, they are both flying straight up. So we got two things flying straight up. Pterodactyl, I don't know. Pterodactyl, big thing. Going up. And then we've got a crow going up. Smaller bird. I'm not drawing birds very well. Also going up. And they're going to have no additional force besides gravity. All right. What will be the speed of the pair after the collision catch? So the pterodactyl is going to catch the crow. So this is going to be an inelastic, completely inelastic collision. Collision should say, momentum, mv plus mv equals mv plus mv, right? Momentum is mv. So little p, momentum is mv, going to be conserved. Remember, in the inelastic case, the two become one thing in the end. And so Let's just write it out. So MA, well, let's do M pterodactyl V pterodactyl 1 plus M crow V crow 1 is going to be equal to M pterodactyl plus M crow, because they're like one unit now, and the second one times the velocity of both of them together, V2. Okay, so I think we have everything except for V2, which is what we're looking for. Alright, so let's just plug in numbers. So mass of the pterodactyl, 50 kilograms, and the pterodactyl is flying 50 meters per second. We're going to have big numbers here. So the mass of the crow is 2 kilograms. The crow is going 35 meters per second. Is going to be equal to the two added together, 50 plus 2 times V2. So V2, let's just calculate this, 50 times 50 plus 2 times 35. 2570 equals 52 V2. So V2, 2570 over 52. V2 is something's wrong here. Let's do that again. 50 times 50 plus 2 times 35. 2570, yes. 2570 divided by 52. There we go. 49.4 meters per second. Alright, so basically almost the same speed as a pterodactyl. Just slowed them down just a little bit and they're going together with a pretty high speed. Okay, the pterodactyl now lets go of the crow 30 meters above the ground while they're still going the same speed. How much higher will the crow go? Assume the crow doesn't fly on its own after the collision. Alright, so the crow is going to be let go, but he's got an initial velocity up of 49.4 meters per second. The crow has mg of, basically his mass was 2, so 2g is his force going down. Alrighty. 30 meters above the ground. Well, they're still going to speed. How much higher will the crow go? Okay, so it's got initial velocity up, and then it's going to keep going up until it stops, and then it's going to start falling back down, right? But there's going to be that turnaround condition here. So let's call this condition 1. When he's 30 meters above the ground and heading up, and then this one up here when he hits the peak and starts to fall again will be condition number 2. Alright, so this one, there's no collision stuff here. It's just the bird is falling up. Anyway, moving up. And so this would be a conservation of energy kind of problem. So let's go KE1 plus PE1 equals KE2 plus PE2. We don't have any non-conservative forces, and so we don't have to worry about, we aren't worrying about air resistance or anything, so we can use this conservation of mechanical energy. KE1, see if we can just write them underneath here, is 1/2 mv squared, so it's going to be 1/2 m 49.4 squared. Right, PE1, I guess we'll take the ground as x equals 0, PE equals 0. Alright, and so he's going to have m, g, and then h. It said he was 30 meters above the ground when the pterodactyl lets go, going up. Alright, that's condition 1. Condition 2, kinetic energy when it's at the top, the peak, and again we're assuming he's going straight up, not going sideways, so 1/2 mv squared, but v is going to be 0 at the peak, right? So kinetic energy 2 is 0, and potential energy 2 is mgh, but we don't know how high he is. That's kind of what we're looking for. So I guess I'm calling that x going up. Did I draw a free body diagram before? Oops, all on this page. Let's call it y instead of x, since it's going up and down. mgy. All right, and that's what we're looking for is y. How high does he go? How much higher? I should have probably called this equals 0. Anyway, we'll have to subtract off 30 in the end here. So let's plug in what we know. 1/2 of 2 times 49.4 squared plus 2 times 9.81 times 30 equals 2 times 9.81 times y. Okay, 49.4 squared plus 2 times 9.81 times 30. So we've got the left-hand side 3,029 joules equals 2 times 9.81, 1962 y joules. So y equals 3029 divided by 1962. $154 meters. Is that right? I guess so. Very high. And so how much higher? So he's 154 above the ground. So how much higher? We'll have to subtract off. So higher is 154 minus the 30 that he was already. So he goes 124 meters higher. Alrighty. What will be the crow's speed when it hits the ground if it doesn't start flying on its own? Alright, so we're going to have a condition number 3. You're going to come back down and get close to the ground. Alright, so if he doesn't start flying, doesn't wake up and start flying, he's going to be in trouble. And so for condition number 3, let's see, we calculated the KE plus PE for condition number 1, so let's just say KE3 plus PE3 is going to be KE1 plus PE1. So all of these conditions, we have no losses, no non-conservative forces, so the kinetic energy is going to be the same. That should be a 1. And so we can calculate the kinetic energy from condition 1 already. So let's just use that again, which is the same for kinetic energy, or for total mechanical energy of condition 2. Either one, they're the same thing. All right, so let's figure out KE3 and PE3. Well, KE3, again, kinetic energy, 1/2 mv squared. We're asked for the crow's speed, so we're asked for V3. We know m. Potential energy 3, when it's at the ground, that's where we said potential energy was 0. Energy is 0, mg y, but y is 0. So potential energy is 0, 3029. So m is 2, so 1/2 of 2 just becomes 1, so V3 squared equals 3029. So V3 square root of 3029. So V3, 55 meters per second. Alrighty, very fast. Don't want to do that, so hopefully he wakes up before he gets to the ground. Oh, and that's the end of the test, sample test. Alright, so hopefully that gives you a good idea of the kinds of things. We've got circular motion kind of problems where we have to remember A equals V squared over R, a few new definitions in terms of velocity. We have some problems with gravity type things, our gravity equation. And then we have energy, conservation of energy, things like this, things like we just did, kinetic energy plus potential energy has to add up and be equal from one condition to the next. And then we have the conservation of momentum, where the MVs on one condition equals MV plus MV on one side equals MV plus MV on the other side. All right, I think that'll do it.